Hello, beautiful human. It's your boy Chad, your favorite galaxy-brained guru taking you to the strangest places in the universe. Welcome back to the channel. So where are you watching from tonight? Are you tucked into bed with the lights off? Maybe you've got some headphones in, lying on the couch after a long day? Or maybe you're one of those legends who puts this on during a road trip and somehow does not fall asleep at the wheel. Wherever you are, I appreciate you. Now settle in and get comfortable, because tonight we are going somewhere truly wild. We are talking about the multiverse. That's right, we're not just exploring this universe tonight. We are exploring every possible universe, every version of reality that could exist, might exist, or, according to some very serious physicists, absolutely does exist. So close your eyes if you want to, relax, and let me take you on a journey through infinity itself. And if it feels right, leave a comment and subscribe for more calming cosmic content. Let's begin. Now, before we dive into the deep end, let us take a moment to understand what we are really talking about when we say the word multiverse. It is one of those terms that has seeped into popular culture through movies, television shows, and comic books, but the actual science behind it is far more fascinating and far stranger than anything Hollywood has dreamed up. At its most basic level, the multiverse is the idea that our universe, everything we can see and measure and detect, is not the only one. There may be other universes out there, perhaps an infinite number of them, each with their own physical laws, their own histories, their own versions of stars and planets, and possibly their own versions of you. That might sound like science fiction, but here is what makes it so compelling. The multiverse is not a single theory. It is a collection of ideas that have emerged independently from several different branches of physics. Quantum mechanics points toward it. Cosmology points toward it. String theory points toward it. These are separate fields, studied by separate groups of physicists, and yet they have each arrived at a similar conclusion, that our universe may be just one chapter in a much larger story. To appreciate why so many serious scientists take this idea seriously, you need to understand a little bit about where modern physics has taken us over the past century. We live in a universe that is approximately 13.8 billion years old. It began with the Big Bang, a moment of extraordinary energy and density from which all of space and time emerged. Since that moment, the universe has been expanding, cooling, and evolving into the vast cosmic web of galaxies, stars, and planets that we observe today. But here is the thing that keeps physicists awake at night. When they look at the fundamental constants of nature, the strength of gravity, the mass of the electron, the energy of the vacuum, they find that these values are exquisitely fine-tuned. If any of them were even slightly different, the universe as we know it could not exist. Stars would not form, atoms would not hold together, life would be impossible. Consider just one example. The strong nuclear force is what holds protons and neutrons together inside an atomic nucleus. If this force were just 2% weaker, protons and neutrons would not bind together at all, and there would be no atoms heavier than hydrogen, no carbon, no oxygen, no life. If it were just 0.5% stronger, nearly all the hydrogen in the early universe would have fused into helium, leaving no fuel for the long-burning stars that our kind of life depends on. Or consider gravity. It is by far the weakest of the four fundamental forces, roughly 10 to the power of 36 times weaker than electromagnetism. And yet, if gravity were slightly stronger, stars would burn through their fuel far too quickly for life to evolve on any surrounding planets. If it were slightly weaker, stars might never ignite at all, and the universe would be a cold, dark void. This raises an enormous question. Why are these values what they are? Is it just luck? Is there some deeper principle that dictates them? Or is the answer something else entirely? That there are countless universes, each with different values, and we simply happen to find ourselves in one where the conditions are right for us to exist? That last possibility is the heart of the multiverse idea. And as we will see, it is not just philosophical speculation. It emerges directly from the mathematics of our best physical theories. So let us begin our journey through the different versions of the multiverse, starting with the one that arises from the most fundamental and well-tested theory in all of physics, quantum mechanics. In the early 20th century, physicists discovered something deeply unsettling about the nature of reality at its smallest scales. When they studied atoms, electrons, and photons, they found that these tiny particles do not behave like miniature versions of the objects we see in everyday life. Instead, they exist in a strange state of possibility until the moment they are observed or measured. Think of it this way. Imagine you have a coin and you flip it into the air. In our everyday experience, the coin is either heads or tails once it lands, but in the quantum world, it is as though the coin is both heads and tails at the same time while it is in the air. It only becomes one or the other when you look at it. This is not a metaphor or an approximation. It is what the mathematics of quantum mechanics actually describes. A particle like an electron does not have a definite position or a definite speed until it is measured. Instead, it exists in what physicists call a superposition, a blend of all possible states simultaneously. The equation that governs this behavior is called the Schrödinger equation, developed by the Austrian physicist Erwin Schrödinger in 1926. It describes how the quantum state of a particle evolves over time, and it does so with extraordinary precision. Every experiment we have ever conducted confirms its predictions. Schrödinger himself was troubled by the implications of his own equation. He devised his famous thought experiment, Schrödinger's cat, to illustrate the absurdity. Imagine a cat sealed in a box with a device that has a 50-50 chance of releasing poison based on a quantum event, such as the decay of a radioactive atom. According to quantum mechanics, until you open the box and look, the atom is in a superposition of having decayed and not having decayed, and therefore the cat is in a superposition of being alive and being dead. Both states are real simultaneously, until the moment of observation. Schrödinger intended this as a criticism, a way of showing that quantum mechanics must be incomplete or misunderstood if it leads to such bizarre conclusions, but the mathematics stubbornly refused to cooperate with common sense. Every experimental test confirmed that superposition is real. Particles genuinely do exist in multiple states at once. But here is where things get philosophically troubling. If a particle can be in a superposition of multiple states, what happens when we measure it? Why do we only ever see one outcome? The standard answer, developed in the 1920s by Niels Bohr and Werner Heisenberg in what became known as the Copenhagen interpretation, is that the act of measurement causes the superposition to collapse. The particle, in a sense, chooses one state, and all the other possibilities simply vanish. Bohr, the great Danish physicist, was comfortable with this. He believed that the quantum world was fundamentally different from the classical world we experience, and that it was a mistake to try to visualize what was happening at the quantum level. The math works, he argued. That is enough. Do not ask what is really going on. For decades, most physicists accepted this explanation and moved on. It became the orthodox view, taught in textbooks and used by working scientists every day. But not everyone was satisfied. Albert Einstein famously objected, declaring that God does not play dice with the universe. He believed that quantum mechanics must be incomplete, that there must be hidden variables beneath the surface that determined outcomes in advance. And then, in 1957, a young physicist named Hugh Everett III proposed a radically different answer. Everett was a doctoral student at Princeton University, working under the legendary John Archibald Wheeler. He was brilliant, unconventional, and deeply bothered by the Copenhagen interpretation. He thought the idea of wave function collapse was arbitrary and ugly. Why should the laws of physics work one way for tiny particles and another way for the act of measurement? Why should observation be special? Everett's solution was elegant and terrifying in equal measure. He proposed that the wave function never collapses at all. Instead, every time a quantum measurement occurs, the entire universe splits into multiple branches, one for each possible outcome. In one branch, the electron goes left. In another branch, it goes right. Both outcomes are equally real. Both branches continue to exist and evolve independently. You, the observer, also split. One version of you sees the electron go left. Another version sees it go right. Neither version is aware of the other. And Schrödinger's cat, under Everett's interpretation, the cat does not face a mysterious collapse. The universe simply branches. In one branch, the cat is alive and well. In the other, it is not. Both branches are equally real. This is the many worlds interpretation of quantum mechanics, and it implies something staggering. Every quantum event that has ever occurred, every interaction between every particle in the universe since the beginning of time, has caused the universe to branch. The number of parallel universes that would exist under this interpretation is not just large, it is incomprehensibly, mind-breakingly vast. We are talking about a number so large that there is no meaningful way to write it down or compare it to anything in human experience. Have you ever wondered what would have happened if you had made a different choice at some crucial moment in your life? A different school, a different job, a different conversation? Under the many worlds interpretation, there is a version of you who did make that other choice, and that version is just as real as the one lying here right now, listening to these words. Now, it is worth pausing here to note something important. The many worlds interpretation is not universally accepted. It remains one of several competing interpretations of quantum mechanics, and there is vigorous debate among physicists about whether it is correct. Some find it extravagant, a violation of a principle called Occam's razor, which says we should prefer the simplest explanation. After all, creating an infinite number of universes every fraction of a second sounds like anything but simple. But defenders of many worlds point out that the interpretation actually adds no new equations or assumptions to quantum mechanics. It simply takes the existing math at face value. The Schrödinger equation already implies all those branches. The Copenhagen interpretation is the one that adds something extra, the mysterious and unexplained process of collapse. From a certain point of view, many worlds is actually the simpler theory. Everett himself had a difficult relationship with the physics community. His thesis was largely ignored when it was first published. Bohr and the Copenhagen school dismissed it. Wheeler, his own advisor, though privately sympathetic, was reluctant to champion the idea too forcefully. Everett, discouraged and feeling rejected by the academic establishment, eventually left physics entirely. He went into defense research, working on mathematical modeling for the Pentagon. He became wealthy, but also reclusive and, by many accounts, deeply unhappy. He drank heavily and smoked constantly. He died of a heart attack in 1982 at the age of just 51, never knowing that his work would eventually become one of the most discussed and debated ideas in all of physics. It was not until the 1970s and 80s, thanks in large part to the tireless efforts of physicist Bryce DeWitt, who gave the interpretation its catchy name Many Worlds, that the idea gained a wider audience and began to be taken seriously by the mainstream physics community. Today, surveys of physicists suggest that a significant minority, perhaps around a third, consider many worlds to be the most likely interpretation of quantum mechanics. There is a poignant detail to this story that is worth lingering on. Everett's daughter, Elizabeth, later said that her father never spoke about his physics work at home. He had completely disconnected from that part of his life. After his death, his son, Mark Oliver Everett, who would go on to become the lead singer of the rock band Eels, found boxes of his father's papers and correspondence in the basement. Mark had barely known his father as a person, let alone as a physicist. Years later, he travelled to Copenhagen to visit the Niels Bohr archive, trying to understand why his father's ideas had been rejected and what they meant. It is a bittersweet reminder that behind every scientific theory, there is a human story, full of ambition, disappointment, and the quiet hope that someone, someday, will understand what you were trying to say. The many worlds interpretation also raises a fascinating question about the nature of probability. In our everyday experience, probability seems straightforward. If you flip a coin, there is a 50% chance of heads and a 50% chance of tails, but if both outcomes actually happen in separate branches, what does 50% even mean? This is called the probability problem in many worlds, and it has occupied some of the best minds in physics. In the early 2000s, the physicist David Wallace at the University of Oxford developed a rigorous framework showing that the standard rules of probability can be derived from the many worlds interpretation using decision theory. His work helped convince many skeptics that the interpretation is mathematically coherent, even if it remains philosophically challenging. Let us now leave the quantum world and turn to a completely different path that leads to the multiverse, one that comes from cosmology, the study of the universe at the very largest scales. In 1980, a young physicist named Alan Guth was working at the Stanford Linear Accelerator Center, puzzling over some deep problems in cosmology. The Big Bang theory was well established by that point, but it had some troubling loose ends. One of the biggest was called the horizon problem. When astronomers looked at the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the entire sky, they found that it was astonishingly uniform. The temperature of this radiation is the same in every direction to an accuracy of about 1 part in 100,000. Think of it like walking into a stadium with 100,000 seats and discovering that every single seat is set to exactly the same temperature, not approximately the same. Exactly the same, down to a fraction of a degree. This uniformity is a problem because, according to standard Big Bang cosmology, regions on opposite sides of the observable universe have never been in contact with each other. There has not been enough time since the Big Bang for light, or any signal, to travel between them. So how did they end up at exactly the same temperature? It would be like walking into two rooms on opposite sides of the planet and finding that both thermostats were set to exactly the same temperature, down to 1,000th of a degree, even though no one had communicated between them. There was also the flatness problem. The geometry of our universe appears to be very nearly flat, meaning that parallel lines remain parallel forever. But the equations of general relativity show that flatness is an unstable condition. Even the tiniest deviation from perfect flatness in the early universe would have been amplified over billions of years into a dramatically curved space. The fact that the universe is still so nearly flat today means that it must have started out flat to an almost absurd degree of precision, something like 1 part in 10 to the power of 60. That is like balancing a pencil on its tip and having it remain perfectly balanced for 14 billion years. Guth's solution was a stroke of genius. He proposed that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion. This expansion, which he called inflation, was far faster than the speed of light. In less than a trillionth of a trillionth of a trillionth of a second, the universe grew from something smaller than an atom to something larger than the observable universe today. This rapid expansion would have taken regions that were originally close enough to reach thermal equilibrium and stretched them far apart, explaining the horizon problem. It would also have smoothed out any curvature, explaining the flatness problem. Guth later described his moment of discovery as the ultimate free lunch, because inflation suggests that the entire observable universe could have sprung from an almost negligibly tiny patch of space. The energy needed to create all the matter and radiation in the universe could have been borrowed from the gravitational field during inflation, making the total energy of the universe potentially zero. Inflation quickly became one of the most important ideas in modern cosmology. It solved several problems at once, and made predictions that have since been confirmed by satellite observations. But as physicists explored the mathematics of inflation more deeply, they discovered something unexpected and profound. The Russian-American physicist Andrei Linde, building on Guth's work in the early 1980s, developed a version called chaotic inflation. Linde, who would go on to become one of the most influential cosmologists of his generation, showed that the inflationary process does not have to stop everywhere at the same time. In fact, in most versions of the theory, it cannot. The field that drives inflation, called the inflaton field, has quantum fluctuations, just like everything else in quantum mechanics. These fluctuations mean that while inflation ends in some regions of space, allowing matter and energy to form and cool into something like our universe, in other regions, inflation continues, and within those still inflating regions, new pockets can form where inflation stops, creating new universes. And in the regions surrounding those new universes, inflation continues still, spawning yet more universes, forever and ever. Imagine a vast, endlessly rising loaf of bread. As it rises, bubbles form within the dough. Each bubble is a universe. Our universe is one such bubble. But the dough between the bubbles keeps rising, keeps expanding, and keeps producing new bubbles, forever. The bubbles are separated by regions of still inflating space, and they may never come into contact with one another. Each one is, for all practical purposes, a self-contained universe. This is the concept known as eternal inflation, and it implies a multiverse of truly cosmic proportions, not just parallel branches of quantum possibility, but physically separate universes, expanding in their own regions of an ever-growing space. The American physicist Alexander Velenkin contributed crucial work to this picture in the 1980s. Working at Tufts University, Velenkin demonstrated mathematically that once inflation starts, it almost inevitably becomes eternal. The conditions that allow inflation to end in one place always persist somewhere else. It cannot be stopped globally. It always continues somewhere. Velenkin showed that the process of universe creation, once begun, never ends. He also contributed a remarkable idea about how the entire process might have begun in the first place, proposing that the universe could have tunneled into existence from literally nothing, not empty space, but the complete absence of space, time, matter, and energy. Through the strange rules of quantum mechanics, he argued, something can indeed come from nothing. Think of eternal inflation like a chain reaction that can never be fully contained. Each new universe that forms is surrounded by regions where the conditions for more universe formation persist. The multiverse, in this picture, is not a static collection of universes. It is a living, growing, endlessly creative process A cosmic factory that has been running for an incomprehensible span of time and shows no signs of ever stopping. There is a wonderful anecdote about Andrei Linde that captures the excitement of this idea. In March of 2014, a team of researchers using a telescope at the South Pole announced what they believed was evidence for gravitational waves produced during the inflationary period, a finding that would have been one of the most important in cosmological history. A colleague at Stanford filmed the moment when Linde was told the news at his front door. The video shows Linde, a white-haired man in a casual shirt, being told that his life's work may have been confirmed. His face transforms from confusion to shock to pure, radiant joy. He embraces his wife, who begins to cry. It is a deeply moving moment. As it turned out, the result was later shown to be contaminated by cosmic dust, and the detection was retracted. But the moment captured on camera remains a testament to the passion and vulnerability of scientific discovery. It is also worth noting just how alien these other bubble universes could be. In our universe, we have 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In another bubble, there might be 5 forces, or 3, or just 1. In our universe, electrons have a specific mass and charge. In another bubble, the equivalent particles might be heavier or lighter, or might not exist at all. Some bubbles might have stable atoms and chemistry. Others might consist of nothing but radiation. Still others might have laws of physics so different from ours that we cannot even begin to imagine what they would look like. And here is where things get even more interesting. Each of these bubble universes can have different physical properties, the fundamental constants, the number of spatial dimensions, even the kinds of particles that exist, can vary from one bubble to another. Our universe has 3 dimensions of space, a specific strength of gravity, and a particular set of elementary particles. But a neighboring bubble universe could have 4 dimensions of space, a completely different strength of gravity, and particles we have never imagined. The physics within each bubble depends on how the inflaton field settles into its lowest energy state in that region, and there may be many different ways for this to happen. This brings us to our next major thread in the multiverse story, one that comes from the most ambitious attempt in all of theoretical physics to unify the fundamental forces of nature, string theory. String theory emerged in the late 1960s and early 1970s, originally as an attempt to understand the strong nuclear force that holds atomic nuclei together. But physicists soon realized it was something far more sweeping. The basic idea is that the most fundamental building blocks of nature are not point-like particles, as the standard model of particle physics assumes, but tiny, vibrating strings of energy. These strings are unimaginably small, roughly 10 to the power of negative 35 meters in length, far smaller than anything we can currently observe. To get a sense of scale, if an atom were blown up to the size of the observable universe, a string would be roughly the size of a tree. The way a string vibrates determines what kind of particle it appears to be. One vibration pattern produces an electron, another produces a quark, another produces a photon. Still another produces the graviton, a hypothetical carrier of gravity. In this way, all the diverse particles and forces in nature are unified as different notes played on the same fundamental instrument. It is a beautiful idea, and one that many physicists find deeply compelling. But string theory comes with a catch, or rather several catches. For the mathematics to work consistently, the theory requires extra dimensions of space beyond the 3 we experience. Depending on the version of string theory, there are either 10 or 11 dimensions in total. The extra dimensions are thought to be curled up incredibly small, far too tiny for us to detect directly. Think of a garden hose viewed from a great distance. From far away, it looks like a one-dimensional line. But up close, you can see that it has a second dimension, the circular cross-section of the hose. In the same way, at every point in our 3-dimensional space, there may be 6 or 7 additional dimensions, curled up into complex geometric shapes called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xingtung Yau, that are too small for us to perceive. Now here is the critical insight that connects string theory to the multiverse. The way these extra dimensions are curled up is not fixed by the theory. They can be folded and twisted into an enormous number of different shapes and configurations. Each different configuration gives rise to a different set of physical laws, different particle masses, different force strengths, a different number of particle families, a different version of physics entirely. How many different configurations are possible? In 2003, physicists Leonard Susskind of Stanford and Raphael Busso of the University of California, Berkeley, estimated that the number is roughly 10 to the power of 500. That is a 1 followed by 500 zeros. To put that in perspective, the total number of atoms in the observable universe is roughly 10 to the power of 80. The number of possible configurations in string theory is so vast that it makes the number of atoms in the universe look like a rounding error. Susskind called this vast collection of possibilities the string theory landscape. Each point in the landscape represents a possible universe with its own unique set of physical laws. And when you combine this with eternal inflation, the picture that emerges is remarkable. Eternal inflation is constantly creating new bubble universes, and string theory provides an enormous menu of possible physics for those universes to have. Put them together, and you get a multiverse in which every possible configuration of physical law is actually realized somewhere. Every combination of particle masses, force strengths, and dimensional structures exists in some bubble, somewhere, in the eternally inflating cosmic landscape. This is a breathtaking idea. It means that somewhere out there, in some distant bubble universe, the laws of physics are slightly different from ours. In another bubble, they are radically different. In yet another, conditions might be just right for some entirely alien form of complexity, or life, or consciousness to emerge, and in most bubbles, the laws of physics probably do not allow for any complexity at all. Most universes in the landscape are likely sterile, inhospitable, and empty. Susskind has argued that the landscape is not a failure of string theory, but one of its most important features. For decades, physicists had hoped that string theory would predict a single unique set of physical laws, the laws of our universe, derived from pure mathematics. The landscape shattered that dream. Instead of one answer, string theory seemed to provide 10 to the power of 500 answers. Many physicists saw this as a devastating blow, a sign that string theory was not the final theory they had hoped for. But Susskind saw it differently. He argued that the landscape provides a natural explanation for the fine-tuning of our universe's constants. We do not need to explain why the constants have the values they do through some elegant mathematical derivation. We simply need to recognize that in a multiverse with 10 to the power of 500 possibilities, some universes will by chance have constants that allow for complexity and life. We find ourselves in such a universe because we could not exist in one that does not support our existence. This reasoning is called the anthropic principle, and while it is controversial, with some physicists considering it an abdication of the quest for deeper understanding, it is taken seriously by many leading researchers. There is yet another way to think about the multiverse, and it comes from a surprising and elegant branch of mathematics and probability theory. Imagine the universe as a vast, perhaps infinite expanse of space. If the universe is truly infinite, and if matter is distributed more or less randomly throughout it, then the laws of probability lead to an astonishing conclusion. Think about it this way. The observable universe, the part we can see, is a sphere roughly 93 billion light-years across. Within that sphere, there is a finite, though enormous, number of ways that matter can be arranged. Each particle can be here or there, moving this way or that. The number of possible arrangements is vast, but it is finite. It is like a cosmic deck of cards. The deck is enormous, but it has a definite number of cards. Now, if space extends infinitely beyond what we can observe, and if the initial conditions of the Big Bang were random, then somewhere out there, incredibly far away, there must be another region of space where the particles happen to be arranged in exactly the same way as in our observable universe. An exact copy. Every atom in the same place, every photon traveling in the same direction, every neuron in your brain firing in the same pattern, and not just one copy. In an infinite space, there would be infinitely many copies. This is sometimes called the Level 1 multiverse, a term coined by the Swedish-American physicist Max Tegmark, who teaches at the Massachusetts Institute of Technology. It does not require any exotic physics. It does not require quantum branching or extra dimensions or eternal inflation. It just requires that the universe be large enough and random enough for patterns to repeat. It is the same principle that guarantees if you shuffle a deck of cards enough times, you will eventually get the same order twice. The distance to your nearest identical copy, if you were to calculate it, would be staggeringly large. Tegmark has estimated it at roughly 10 to the power of 10 to the power of 29 meters. That is a number so large that writing it out in full would require more digits than there are atoms in the observable universe. But in an infinite cosmos, even staggeringly large distances are traversed eventually. Somewhere, inconceivably far away, there is another version of you, listening to these exact words, in an identical room, on an identical night. Tegmark has gone further than most in his classification of possible multiverses. Beyond the level 1 multiverse of distant copies, he proposes a level 2 multiverse corresponding to the bubble universes of eternal inflation, a level 3 multiverse corresponding to the many branches of quantum mechanics, and a level 4 multiverse, which is perhaps the most radical idea of all. The level 4 multiverse is the idea that every mathematically consistent structure exists as its own physical reality, not just every possible configuration of the same physical laws, but every possible set of laws, every possible mathematics. If a set of equations is self-consistent, then somewhere, somehow, it describes a real universe. Tegmark calls this the mathematical universe hypothesis. He argues that physical reality does not merely have mathematical properties, it is a mathematical structure, and every such structure is equally real. This is an extraordinary claim, and it blurs the line between physics and philosophy in a way that many scientists find both provocative and deeply uncomfortable. It raises questions about what we mean by existence, reality, and explanation, but it also has a strange internal logic. If you ask why the physical world obeys mathematical laws, the mathematical universe hypothesis provides a simple answer, because the physical world literally is mathematics. Now, all of this raises an obvious and important question. Can any of this be tested? Is the multiverse a scientific theory, or is it just speculation dressed up in mathematical language? This is one of the most heated debates in modern physics, and honest, thoughtful people disagree. The traditional standard for a scientific theory, going back to the philosopher Karl Popper in the mid-20th century, is that it must make testable predictions. If you cannot design an experiment that could, in principle, prove the theory wrong, then some argue it is not really science at all. The multiverse at first glance seems to fail this test. We cannot travel to other universes. We cannot observe them directly. We cannot send a signal to them or receive one back. So how can we ever know if they exist? But the picture is more nuanced than it first appears. While we may never observe other universes directly, the theories that predict them, quantum mechanics, inflation, string theory, do make testable predictions about our own universe. If those theories are confirmed to ever greater precision, that lends indirect support to their other implications, including the multiverse. You cannot pick and choose which predictions of a theory to accept. If a theory's tested predictions all check out, you have to take its untested predictions seriously as well. Consider inflation. The theory of cosmic inflation predicts a specific pattern of tiny temperature variations in the cosmic microwave background radiation. These predictions were confirmed with remarkable precision by the WMAP satellite mission, launched in 2001, and the Planck satellite mission, launched in 2009. Inflation also predicts that these temperature variations should follow a nearly scale-invariant spectrum, meaning that the variations look roughly the same on large and small scales. And they do. Every test of inflation that we can perform in our own universe has been passed, and eternal inflation, which implies the multiverse, is a natural and, some would argue, inevitable extension of the same physics. Similarly, some versions of the multiverse make statistical predictions. If we live in a multiverse where the cosmological constant, the energy density of empty space, can take many different values, then the anthropic principle predicts that we should observe a value that is small enough to allow galaxies to form, but not necessarily zero. In 1987, the Nobel Prize-winning physicist Steven Weinberg used this reasoning to predict that the cosmological constant should have a small but positive value. At the time, most physicists believed it was exactly zero. Weinberg was going out on a limb. A decade later, in 1998, two teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rice, made one of the most shocking discoveries in the history of science. By studying distant supernovae, they found that the expansion of the universe is not slowing down, as nearly everyone had expected. It is speeding up. The universe is accelerating, driven by a mysterious repulsive force now called dark energy. The measured value of the cosmological constant was small, positive, and remarkably close to what Weinberg had predicted using multiverse reasoning. All three astronomers received the Nobel Prize in Physics in 2011 for this discovery. This is not definitive proof of the multiverse, but it is suggestive. It is the kind of evidence that makes scientists sit up and take notice. A prediction was made based on multiverse reasoning, and the prediction turned out to be correct. Other potential lines of evidence are more speculative but tantalizing. Some physicists have proposed that if our universe is a bubble within a larger multiverse, there might be subtle signatures of collisions with neighboring bubbles imprinted in the cosmic microwave background. These would appear as faint circular temperature anomalies in the sky. Teams of researchers have searched for such patterns, and while no definitive evidence has been found, the search continues with ever more sensitive instruments and more sophisticated analytical techniques. There is also the possibility that advances in quantum computing might shed light on the many worlds interpretation. The physicist David Deutsch has argued that the power of quantum computers comes from their ability to perform calculations across multiple branches of reality simultaneously. If quantum computers can perform certain calculations that would be impossible in a single universe, that might be seen as indirect evidence that computation is somehow being distributed across multiple branches of reality. This is a speculative idea, and not all physicists agree with this interpretation, but it illustrates the creative ways in which researchers are thinking about how to probe these questions. It is also worth mentioning the ongoing debate about what kind of evidence should count when it comes to the multiverse. The physicist George Ellis, a distinguished cosmologist who collaborated with Stephen Hawking on the study of the large-scale structure of space-time, has been one of the most vocal critics of the multiverse. He argues that the multiverse is not truly scientific because it cannot be directly tested, and that accepting it as real represents a fundamental shift in what we mean by science. He worries that if physicists embrace untestable theories, the field will lose its grounding in empirical reality. On the other side, physicists like Sean Carroll of Johns Hopkins University argue that science has always involved reasoning about things we cannot directly observe. We cannot see quarks. We cannot see the interior of a black hole. We cannot see the Big Bang itself, but we accept these things as real because they are implied by theories that make successful predictions about things we can observe. The multiverse, Carroll argues, is no different. It is what the math tells us, and the math has earned our trust. This is one of the great intellectual tensions of our time. The multiverse sits right at the boundary between physics and philosophy, between what we can know and what we can only infer, and reasonable, brilliant people disagree about which side of that boundary it falls on. Let us also consider what the multiverse means for some of the deepest questions we can ask. Questions about meaning, purpose, and our place in the grand scheme of things. If the multiverse is real, it changes the way we think about our own existence in subtle but important ways. We are not inhabitants of the only reality. We are inhabitants of one reality, among perhaps infinitely many. The particular arrangement of atoms and forces that makes up our world, our sun, our planet, our bodies, our memories, is just one of countless possible arrangements. And yet this arrangement is the one that gave rise to consciousness, to curiosity, to music and mathematics, and the capacity to wonder about the nature of reality itself. There is something both humbling and awe-inspiring about this. Humbling because it reminds us that we are not at the center of everything. Think about the history of our self-understanding. Humanity once believed the Earth was the center of the cosmos. Then Copernicus showed us that the Earth orbits the Sun. Galileo confirmed it with his telescope. Later, astronomers discovered that our Sun is just one ordinary star among roughly 200 billion in the Milky Way galaxy. Then they discovered that our galaxy is just one among 2 trillion galaxies in the observable universe. Each discovery pushed us further from the center, further from any special status. The multiverse, if it exists, takes this one step further. Our entire universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, may be just one among an incomprehensibly vast, perhaps infinite, collection of universes. We are not at the center of the Earth, not at the center of the solar system, not at the center of the galaxy, not at the center of the universe, and perhaps not even in the only universe. And yet it is also awe-inspiring, because out of all those possible realities, this is the one where we exist. This is the reality where matter organized itself into stars that forged heavier elements in their nuclear furnaces, where those elements condensed into rocky planets, where chemistry produced self-replicating molecules, where evolution produced brains, where neurons connected in just the right way to produce thought, wonder, love, and the ability to ask why. Have you ever noticed how a clear night sky can make you feel both incredibly small and incredibly connected at the same time? The multiverse takes that feeling and amplifies it to an almost unimaginable degree. You are a tiny part of an incomprehensibly large whole, and yet you are a part of it. You are the universe, or perhaps the multiverse, becoming aware of itself. Some scientists and philosophers find the multiverse unsettling. They worry that if everything is possible somewhere, then nothing is truly special. If every choice leads to every outcome in some branch of reality, does choice even matter? If there are infinitely many copies of you, are you still unique? But others see it differently. The physicist David Deutsch, one of the pioneers of quantum computing and a passionate advocate of the many worlds interpretation, has argued that the multiverse actually makes our choices more meaningful, not less. In his view, the fact that every possibility is explored somewhere does not diminish the significance of what happens in our own branch. We still experience our lives, we still make decisions, we still feel the consequences. The existence of other branches does not erase the reality of our own experience any more than the existence of other people erases the significance of your own life. Your joys are still your joys. Your struggles are still your struggles. The multiverse does not take that away. The philosopher and physicist Sean Carroll has put this beautifully. He suggests that the multiverse, rather than making existence feel meaningless, can actually help us appreciate the preciousness of our particular experience. In an infinite landscape of possibility, the specific thread of reality that you are living through right now, this exact sequence of moments, choices, and experiences is unique to you. Even if other versions of you exist elsewhere, they are living their own stories. Your story is yours. Think of it like a library containing every possible book. The existence of all those other books does not make the one you are reading any less meaningful. The words on the page in front of you still have the power to move you, to teach you, to change the way you see the world. The multiverse is the grandest library imaginable, and you are reading one very particular page. There is one more perspective worth considering before we close. The physicist John Archibald Wheeler, who mentored Hugh Everett and who made enormous contributions to our understanding of gravity and quantum mechanics, spent the last decades of his life thinking about the relationship between observation and reality. He developed an idea he called the participatory universe, the notion that the universe does not fully exist until it is observed. In Wheeler's view, consciousness is not a passive bystander in the cosmos. It is an active participant. The universe, he suggested, is a self-exciting circuit that brings itself into being through the act of observation. We are not just in the universe. We are how the universe knows itself. Whether or not Wheeler was right in the details, the spirit of his idea resonates deeply with the multiverse. In a reality that may be vast beyond comprehension, awareness matters, curiosity matters. The simple act of wondering, of asking what is out there and what it all means, may be one of the most significant things that happens in any universe. As we draw this exploration to a close, let us take a moment to reflect on where we have been tonight. We started with the strange behavior of quantum particles, and Hugh Everett's daring proposal that the universe splits with every quantum event, creating an endlessly branching tree of parallel realities. We traveled to the earliest moments of the cosmos, where Alan Guth's theory of inflation suggests that our universe is just one bubble in an endlessly frothing sea of creation, and where Andrei Linde and Alexander Vilenkin showed that this process of universe creation may never end. We ventured into the mathematical abstractions of string theory, where Leonard Suskind's landscape revealed a staggering 10 to the power of 500 possible physical realities. And we considered the simple but profound idea, championed by Max Tegmark, that in an infinite universe, everything that can happen does happen, somewhere. Each of these paths to the multiverse is different. They arise from different areas of physics, different mathematical frameworks, different sets of assumptions, and yet they converge on a similar vision that reality is far larger, far richer, and far more astonishing than our everyday experience would suggest. We do not yet know if the multiverse is real. We may never know for certain. The question may ultimately be one that science cannot fully answer, at least not with the tools and technologies we have today. But the fact that our best theories point in this direction is itself remarkable. It tells us that the universe, or the multiverse, is under no obligation to be simple, small, or easily comprehensible. It can be as vast and as wild as the mathematics allows, and the mathematics, it turns out, allows for quite a lot. And so, as you lie here in the quiet of this moment, consider this thought: of all the possible realities that might exist, of all the possible arrangements of matter and energy and physical law, You are here, in this one. You are conscious, you are aware, and you have just spent the last hour contemplating the deepest structure of existence itself. That is not a small thing. That is extraordinary. The universe, however many versions of it there may be, produced you. It produced your curiosity, your wonder, your desire to understand, and in a cosmos that may be infinite, in a multiverse that may contain every possibility, the fact that there is something rather than nothing, the fact that there is a you rather than an empty void, is perhaps the most remarkable thing of all. Not the multiverse itself, but the fact that within it, something arose that could imagine it, something that could lie still on a quiet night, listening to words about infinity, and feel even for a moment the weight and the wonder of what it means to exist. Let that thought settle gently as you drift. The questions do not need answers tonight. They just need to be felt, the way you feel the warmth of a blanket or the rhythm of your own breathing. The vastness is not something to fear. It is something to rest inside, like a warm and endless night, full of stars you will never finish counting, and that is perfectly fine.